in here, and Henrik Engström for the other 40% that doesn't speak Swedish. That was proven yesterday. My title is Architect at Kindred, and today I'm going to present distributed SQL databases and why I think they are awesome. To do so, I'm going to introduce CockroachDB, and CockroachDB is a database that's inspired by Spanner. So I'd like to check how many of you have heard of Spanner before. That's around 10%. And CockroachDB? A little more. Interesting. Okay, yeah, great. So hopefully my intention today is to provide you with a better overview of the landscape of what's possible with databases in the term of building distributed global systems, and that you don't just have to go to the NoSQL databases to do so, but you can stay in the beautiful SQL land and still enable these properties. As I said, I work as an architect at Kindred, and Kindred is a company, an umbrella company, and underneath we have 11 different brands. It started as Unibet back in 1997. We are making money, which is, of course, very important, but more important, or equally important as a software engineer, is that we have a lot of users. We have around 25 million users. And 25 million users, as you understand, can generate a lot of load. So we have lots of transactions. We, a comparison to PayPal, quarter 2 2019 had around 3.1 billion transactions, and we're around 2.7 billion transactions, so almost on par with PayPal. And to handle that kind of traffic, we have decided to have a microservice-based, event-driven architecture based on Java. We have around 250 microservices, and some of them are point-to-point, but most of them are emitting messages, so it's event-driven. Anyone who's interested in something going on at a platform can subscribe to those events and then react upon them. We're around 1,500 employees. We're 500 in tech. We have some tech hubs all over the world. We're always looking for great colleagues, so feel free to follow that link and see if there's anything for you. We operate in 3 continents. We have offices in the US. I'm based in New York City. We have offices all over Europe, and we're also in Sydney and Darwin. A little bit about me. I started programming 36 years ago. I wrote my first basic program 36 years ago. I wrote my last basic program 36 years ago. No, not really. It was a good beginner's language. But I've been programming since then. I started as a professional developer in 1998 as a consultant here in Stockholm, dabbling around in gambling, finance, and retail. I did so for the odd 13 years or so. And then I moved on to a company called TypeSafe that later became Lightbend, where I worked with a programming language called Scala and ACA, which is a fantastic toolkit, and observability. And last year, I moved on to become an architect at Kindred. So today's agenda, I've divided these presentations into 4 sections. First, we're going to start to look at challenges with data consistency. And this is where I set the stage to get you to understand where we come from. The journey from basically mainframe to cloud. We're going to take a look at the CAP theorem, which I'm sure most of you have heard before. I'm going to discuss a very influential paper in this domain, and then a slide on ACID and something called ACID 2.0. And then we move on to data consistency definitions. Here, I'm going to describe strong consistency, from strong consistency down to eventual consistency, and describe some levels in between those two. And we're also going to talk a little baseball. The application tier section is going to describe the problems that arise, or mitigations of the problems that arise when you can't use ACID transactions. That is going to just be a slide or two, but it gives you an understanding of what you can do to mitigate that. And then finally, the biggest section is NewSQL, a slide with definitions of what I think NewSQL is. And then we're going to take a look at one of these awesome databases called CockroachDB. There's also going to be some quotes from Google to support what I think here. Let's start off with challenges with data consistency. So why is data consistency a problem in the first place? Well, if you think back a few years, or 20, 30 years, all we had was one server that we deployed the software to. So we didn't have to think about network hops. We didn't have to think about latency. We didn't have to think about services not responding. We didn't have to think about time being different on different servers, because that's the reality. As you know, clocks are inherently unreliable unless you use special hardware for it. So that was not a problem when we deployed on these type of, well, this is not a server, but these type of hardware. The only problem we basically had, or one of the biggest problems, was that when the server crashes, we no longer have a system. And that's a big problem. So people started thinking about this and deploying onto multiple servers. And this trend started way back, but it really picked up in I'd say in the mid-2000s. So looking at this graph first, we have the green line is number of transistors, and you can see it's increasing, not linearly, but even more than linearly, almost exponentially. The blue dots, the dark blue dots, is the clock speed. So you can see around 2004 or so, the CPUs didn't increase their clock speed. We still had the growth of transistors, so that led to the CPU single core becoming multiple cores. And at the same time, as a result of that, we no longer had the big monolith hardware. Back in the days, what we could do before this trend, before 2004, if you had a slow system, all you had to do was to wait 18 months, and the system would execute almost twice as fast, and the hardware would be half the price. That no longer held true around 2004 and forward, so we went from big monolith to smaller servers. And that also, there was another trend, on-prem to cloud. AWS was launched March 2006, and as a result, we started to deploy distributed systems. And companies started to realize in this distributed environment, we can no longer rely on RDBMS systems and transactions. So that started this trend of eventual consistency, and NoSQL was coined. And NoSQL, as you know, have a couple of categories in them. We have the wide column database types, Cassandra. We have document databases, MongoDB. That's if you need web scale. We have Couchbase, key value store, and Neo4j, which was presented yesterday as a graph. All of these are very specific for a specific domain. What they have in common is that they don't support SQL, so hence the name. And then finally, the CAP theorem was coined. CAP was coined in 2004, but it actually originates or appeared already back in 1998, according to Eric Brewer at Berkeley University. And just a quick rehash of the CAP theorem, you have consistency and availability and partition tolerance. And consistency means strong consistency, the highest order of consistency. Availability, you have to have 100% availability for reads and writes. And partition tolerance, you should be able to support full tolerance of network partitions. And it's generally viewed that it's inevitable to not have network partitions. So you can only pick one of consistency and availability. So you have CP systems like Oracle and MySQL, and then you have AP systems like Cassandra and Couchbase. So the trend of understanding CAP started mid-2000s, and a lot of companies started thinking about this because they were experiencing higher and higher loads. They had to distribute their systems to cope with this load. And companies like AWS started to think, okay, how can we cope with this? And one of the astute people at AWS, Pat Helland, wrote a paper. And that paper is called Life Beyond Distributed Transactions, an apostate's opinion. And what's important here that I want to highlight is beyond, the word beyond, and apostate. And an apostate is a person that renounces his or her religious or political belief or principle. So basically what Pat is saying here, he believed in transactions, but he no longer believes in that. The paper has such an impact on our industry, so I think it's worth to go through a few quotes. And I'm going to start off, this is at the beginning of the paper, and it says, "Personally, I've invested a non-trivial portion of my career as a strong advocate for the implementation and use of platforms providing guarantees of global serializability." Okay, so he's now, if you think about a title, Beyond Transactions and Apostate, but he starts the paper by saying he wanted this to work. He wanted to believe in transactions. But if we continue to read in the paper, there's this quote, and it's, "In general, application developers simply do not implement large scalable applications assuming distributed transactions. When they attempt to use distributed transactions, the project founder, because the performance cost and fragility make them impractical." So here he stipulates that if you're using distributed transactions in a globally scalable system, then you're going to pay a performance cost, and your system is going to be fragile. Okay, so we no longer can use transactions because it's clear from this paper. What can we do instead? Continuing to quote from the paper, and this is the third and final quote, it says, "In a system which cannot count on distributed transactions, the management of uncertainty must be implemented in the business logic." So here Pat says that we can no longer rely on our databases to take care of transactions. Instead, we as engineers must now take care of this. So we're pushing the problem up to the business tier. And that, of course, I mean, as engineers, it's a cool problem. I mean, it's a very interesting domain, but maybe it's not the core business of the company you work for. And I want to park this thought for now, and then we're going to go back in later in the presentation and look at what Google thinks about this. But what Pat's paper did, it made the engineers aware of, to reach true global scalability, you have to basically get rid of transactions. So there was an evolution of consistency. We went from strong consistency. You all have heard about ACID, and ACID was actually coined as a term in 1983, but it was supported by IMS in 1973. And ACID, as you know, stands for atomicity. It's all or no operations. Consistency, no violation of constraints. Isolation, you have exclusive access to the data you operate upon. And durability, if there's a server crash, you can always get back to where you were before. Now, with this trend of eventual consistency in mid-2000s, someone was clever and think about, wait, everyone knows about ACID. I'm going to create an ACID 2.0 acronym. So that was done, and ACID 2.0 stands for associative, and that basically means that the order of applying functions do not matter. So if you do set add 1, add 2, that's the equivalent of doing set add 2, add 1. And then we had commutative, and that's what the arguments, arguments are order insensitive. So if we do math max 1, 2, that's equivalent of doing math max 2, 1. And then idempotent, that's a function returns the same result regardless of number of invocations. So using a map again, map put A1 is equivalent of doing map put A1. And the final, the D stands for distributed. That's more of a symbolic meaning, but it highlights the fact that ACID 2.0 applies onto distributed systems. Okay, so let's move on to data consistency definitions. I mentioned baseball, and what has baseball got to do with this? Well, the reason for this, or the inspiration for this, is a great paper by a person called Doug Terry at Microsoft called Data Consistency Explained Through Baseball. I know baseball is not the biggest sport in Sweden, so I'm going to try to explain the rules a little by using Scala code. For anyone who is a baseball geek, yes, this is not the full set of rules. I understand that. But basically what we have a class team that has a name and some points associated. And then we have a method, add point, that we can call and increment the points. We're also passing on the inning the point was scored in. If we look at the rules, we have 2 teams in a baseball game. And we run something called innings, 9 innings. You can think of innings as periods. And in each period, there's going to be the visitor team is going to start, and the visitor team can try to score points as long as they don't have 3 outs. So 3 outs, an out would be if someone gets burned on the base before they get to a base when they run, or if you catch the ball, that would be an out. But if they score, if a person is able to run to the 4th base, that's a point for the team that's playing, for the team that's batting. Okay, so when the visitor team has 3 points, then it's the home team's turn, and you just keep on going. So this is an oversimplification, but that's about it. So we should now play a game of baseball together. So what I want you to suppose here is that we have a key value store that holds the total points somewhere in the cloud in multiple servers. And then we have different read guarantees from the client's perspective, and we're going to see what happens when we read with different guarantees. And just before we go through that, I want to explain what the scorecard here says. So we started with, obviously, the score 0-0, and the visitors got to start in the 1st inning. And they didn't score a point. The home team in the 1st inning scored a point, so we emit that as an event. And then the 2nd inning, no one scored. And in the 3rd inning, the visitors team scored 1 point, and the home team scored. So on and so forth. And we're now in the 7th inning, and the home team, it's the home team's try now to score points. And applying this to different levels of consistency, if we look at strong consistency, that can actually just return one result, and that's the current score. And the current score is visitors to home team 5. So 2-5 is the current score. If we look at the eventual consistency, then you can get 1 of 18 results. And that's really interesting. We can get 0-0, of course, and we can get 0-1. Well, that's a given. But we can also get 0-2, 0-3, 0-4. And what's interesting here is, if you look at the game, at the scorecard again, 0-2 never happened in the game. Because in the 3rd inning, the visitor team scored 1 point. So the true score is 1-1, but still with eventual consistency, because we can't guarantee the order of the events that are being received on the server side with eventual consistency. So we can get results that never happened. With consistent prefix, this is similar to snapshot isolation. We're going to see a true result, but we're going to see it sometime back in some period back in time. So we don't know exactly how out of date this is, but we know it's a true result. So 2-3 actually happened. All of these results happened in the game. It's just we don't get 2-5. And for monotonic reads, that's similar to eventual consistency, but we know we're not going to get an outdated result. We're not going to get an older result than the one we have. So here we can still get incorrect results, but we know we're not going to get any old data. And finally, read your writes. Read your writes is the writer is always going to see, it's also called read my writes in some literature. The writer is always going to see the result it wrote. So if we write 2-5, we're always going to get 2-5 back. But for everyone else in the system, it's actually eventual consistency. So the 4 bottom ones are actually all some form of eventual consistency. But the 3rd bottom ones have some stricter rules. It's not true eventual consistency, but it's kind of eventual consistency. So we're going to now apply this to some different participants or actors in the baseball game. So if you think of the official scorekeeper, the official scorekeeper is the one writing the result, right? So they see a score, they write it down, and the next time there's a score, they want to check with the system what the score is, and they get back what they wrote. So for them, it's actually enough if we have read my writes as consistency level. If we move on to the umpire, which is the referee, well, the referee doesn't actually care about the score and the game up until 1 point, and that's after the visitors are done in the 9th inning. And if it happens to be that the visitors have lower score than the home team, then the home team have won. So no need to continue the game. It's actually over at that point. So for the umpire, that person needs to know exactly what it is at that point in time. So that's going to be strong consistency. For radio reporting, let's say we have a radio program where we announce the results every 30 minutes. So outdated results are, of course, fine. but it can't be an incorrect result. We can't use eventual consistency. We can't say, well, the score was 0.5, because that never happened. So it wouldn't be an honest broadcast. It would be fake media, actually. What we can use here instead is monotonic reads plus consistent prefix. And why can't we use consistent prefix for this? Well, if we read from different servers, they might have different results. So if we read, 1.3, and then we can read an outdated result after and report 1.2 the next time we report. So that's not enough. So if you combine monotonic reads and consistent snapshot, then we have enough consistency for that, or consistency level. If we move on to the statistician, they must know the result they're marking down is actually true. So for them, it would be strong consistency. And finally, for a stat watcher, someone who's subscribing to some website where they go in a week later and check the stats, people who love baseball also love statistics. For them, it's perfectly fine to have eventual consistency. So you can see, based on what role you have in the baseball game, that you can use different levels of consistency. If you're interested in consistency models, then this overview here is fantastic. I'm not going to go through all of these, but it's created by a person called Kyle Kingsbury, also known as Afer on Twitter. He has a company called Jepsen, and Jepsen, what they do is they try to disprove companies who claim they have some sort of consistency, a distributed system and some consistency level. And what he does is he goes in and he absolutely hammers the system. He has a test suite, and he tries to disprove their claim. So I was at one conference in Chicago a few years back where he likened Elasticsearch as a pile of burning towers, and then Elasticsearch was like this wooden structure on top of that. That might not be true any longer, so don't quote me on that, but that was the consistency level they claimed, that was a pile of burning tires, which is interesting. So in here he describes the level, different levels. So strict serializable is the top one, and then they're all related, and you can go in and read about different ones like causal consistency here. Causal consistency is something we used a lot in tracing, when I work with tracing and observability, where you have traces, events that are generated on different servers, and time is not used, but you can still relate these by using 3 IDs. So you can use a transaction ID, a parent ID, and your local ID. And if you're down the chain, you're always going to refer to the parent ID. And the first event that's submitted just creates the transaction ID. So that's building a tree, and you know the relationship. If you point back to the parent ID, you know that happened after, because that parent ID, that ID needs to exist for that to happen. And based on that, you can actually make sense of what's going on in your system. Obviously, not using time. So remember when I talked about Pat, and he said we're pushing this uncertainty onto the engineers now. That's what I call the application tier consistency. And we're going to take a look at, I have a few slides on application tier consistency. I realized this might be too small here, so I'm going to read it out loud, but it's a comic strip where the lady says, Kitty's stuck in a tree, and the superhero comes in, and she asks him, do you think you could climb all the way up there? And he's like, no need, and he picks the cat up from the bottom one. And then she's like, thank you, wait, now I have two cats. And he's like, yeah, don't worry about that, it's going to be fine after a while. And then the final one, there's only one cat. And this, I think, describes one issue with eventual consistency. And I've been to a lot of conferences where people say, hey, you want to build a highly scalable distributed system? That's easy. Just sprinkle some of this stuff onto your design and you'll be fine. And I mean, in all honesty, that is true. Yes, it is possible. I've used all of these techniques and patterns, and I would say successfully so, but it's quite difficult to do so, and it's a burden on the engineers. So, because you have to understand, the core foundation here, of course, is eventual consistency, events flowing back and forth. But you also have to apply a few other techniques. So we have idempotency. I already discussed that. That's where you can call a function multiple times, but you know the result is never going to change beyond the first invocation of that. And that's really useful. And I would strongly suggest that you apply this pattern, especially if you're using a microservice architecture, and if you're event-driven, because messages will be delivered multiple times. So your system has to, or your service has to understand that this message that I'm now receiving can be sent further down the line. So idempotency is very important. Another technique here is CQRS, command and query responsibility segregation. That's basically where you have a write side, the command side, and a read side, the query side. And what you can do is the write side just writes, of course, and then it emits events over to the read side, where you can store the data in some denormalized fashion to provide for quick reads or fast reads. But there will be a lag between the write side and the read side, so that's eventually consistent again. And your system needs to understand, you need to take that into account. But obviously, you can build a quite scalable system by applying those techniques. There's also something called conflict-free replicated data types, and that's basically data types that can be updated independently and concurrently without any sort of coordination. And that's very effective, but it doesn't apply to all the domains you're in. And finally, the Saga pattern, and that basically enables business transactions in an event-driven architecture, but you have to implement that yourself. So what can we do instead? If we don't want to go down this route and we still want to be scalable and distributed, well, we can look around for alternatives. One alternative is CockroachDB. Before I go into CockroachDB, though, I would like to describe something called NewSQL. So we went from SQL to NoSQL, and now we have NewSQL. This was coined in 2011. The idea here is to still support the relational model. The lesson learned was, well, actually, SQL is pretty good to have. A lot of engineers know SQL. It's good to do joins of tables and what have you. And actually, ACID transactions are also quite good to have. So that's no difference from MySQL or Oracle, what have you. The difference with NewSQL is that they also support resilience, and they scale horizontally. So how can they do that? I mean, what's different now from then? Well, someone came up with a brilliant idea to actually split the database into so-called chunks. And instead of using the consensus protocol on the full database, you just run the consensus protocol on those chunks. So we're going to look how Cockroach does this. So a few examples of NewSQL databases. The flagship, Spanner DB, Google. Google run a lot of their core systems on top of Spanner. And that's really interesting. I mean, if Google can get away with this, then I think most of us can get away with it. Another database that's really interesting is Cosmos DB from Microsoft. That's in Azure. What's interesting here is you can decide what level of consistency you want to use. So they provide 5 different categories of consistency. So everything from eventual to strong consistency, which is linearizable in their case. And then CockroachDB, of course. So before we go into CockroachDB, I promised a few quotes from Google. This is from their brilliant paper, Spanner, Google's globally distributed database, 2012, so 5 years after Pat's paper. We believe that it's better to have application programmers deal with performance problems due to overuse of transactions as bottlenecks arise, rather than always coding around the lack of transactions. So if you remember what Pat said, he said, when they attempt to use distributed transactions, the project founder, because the performance cost and fragility make them impractical. Here we have AWS. It's a beef between AWS and Google. Google has come to the complete opposite conclusion on this topic. And I always say, if Google engineers find it too difficult to not use transactions, then I think most companies will suffer from that too. Another quote from another paper, Life on Cloud Spanner Reads and Writes. Within Google, we've found that this, strong guarantees, has made it significantly easier to develop applications on Spanner compared to other database systems with weaker guarantees. When application developers don't have to worry about race conditions or inconsistencies in their data, they can focus on what they really care about, building and shipping great applications. So I went through a few quotes from Pat papers, and I left one out. In the end of the paper, he says, real-world, almost infinite scale application would love the luxury of a global scope of serializability, as is promised by two-phase commit and other related algorithms. So basically, I think Google and Pat were in agreement here. They would love that. What the difference was back in 2007, no one had come up with a technique to basically achieve this. We're going to revisit the CAP theorem. Remember, when we talked about availability, it was 100% availability. What's 100% availability? Nothing, right? There's no such thing. So we can instead talk about realistic high availability, and Spanner claims to therefore be a CA system, a consistent and available system. Technically, it's still a CP system, consistent and partition tolerant, but they call it effectively CA. And the reason they can do that is because Google have invested a lot in their infrastructure, so they have redundancy everywhere. So they promise 5 nines uptime, and that's equivalent to 5.5 minutes downtime per year, and therefore they say, we're effectively a CA system. So this kind of, I think this claim is true, and I think it's good to have this lens on top of these type of systems as well. Let's move on to Cockroach, because that's why we're all here, right? Cockroach is a formally open source database based on and inspired by Spanner concepts. The 3 founders of Cockroach all happen to come from Google, so they're ex-Googlers. The reason why it's formally open sourced, if you download this, you can follow that link, and they have a blog post on Cockroach Labs, which is their company, where they explain why they're no longer open source. And the main reason for that is there are companies out there taking open source software and cloudifying it, and then offering that as part of their own product suite. And they're giving $0 back to the company who've actually built this stuff. And this is a problem in our industry, that no one's giving back to open source. Most of these big companies out there, they wouldn't be where they are unless it was for open source, but it so just happens that they don't care about that, and they just monetize open source. So basically this prohibits, their new license prohibits companies from taking their stuff and cloudifying it. I'm going to go through a few CockroachDB highlights here. It's a distributed, replicated, transactional key value store in the bottom. And they used to use RocksDB, for those of you who know that. They now have implemented their own implementation called Pebble. And Pebble is a smaller, it has a smaller function set, specifically targeting the Cockroach needs. And it's also a little more performant for their needs. Internally, they're using so-called ranges. These are the chunks I talked about before. And we're going to take a look at a little more detail on ranges. And they're using RAFT, the RAFT protocol for consensus. The link here links to a really cool animation of how RAFT works, if you're interested in that. You don't have to use atomic clocks. For Spanner, their whole infrastructure is built around atomic clocks and GPS. So they can guarantee that no server, Google has servers worldwide, no server differentiates more than 7 milliseconds. And with NTP, that's impossible to do. NTP, you're probably around 250 milliseconds sometimes. Instead of atomic clocks, they're applying hybrid logical clocks and NTP and Cockroach. Cockroach provides geo-distribution capabilities. What's meant with that is you can locate the data into specific regions, and we're also going to take a look at that. Cockroach comes with full SQL support. They support the PostgreSQL dialect. They have something called change data capture, and I've linked to the outbox pattern here. It's a good blog post for what this pattern does and means. It's been Jepsen tested. They actually failed the first Jepsen test. He's like, guys, what are you doing? It doesn't work. But they sorted that out and said, hey, can you please come back and try it out again? And now they're approved. And finally, CockroachDB, although you can use it on-prem, it comes with a cloud-native version, so you more click and deploy into AWS and GCP. Let's take a look at ranges and replication. So these ranges are 64 megabytes in size. The reason for that is they're small enough to quickly move around, but they're also large enough to amortize the cost of consensus. Each of these ranges will be on a minimum of 3 nodes, and each range is a RAFT group. They have something called leaseholders, and leaseholder is going to be one in these ranges. So one range is going to have one leaseholder, and the leaseholder is the one that controls the reads and the writes. So whenever you're writing to a range, it's going to go through the leaseholder, and whenever you're reading, it's going to come from that leaseholder. And by doing that, they can guarantee that the data is up to date. They have something called follow the workload, and follow the workload basically means that the range holders, the leaseholders, can move around in your cluster. And to do so, they have a pretty cool algorithm, a replica placement algorithm, so they understand how to place the nodes in the cluster. And here they look at space. They want to utilize the disk in your cluster as well as possible. They have diversity. They want to spread your replicas outside of failure domains. So if one domain is down, you still have the data. They want to load the system or look at load, and that particularly is to look at where the leaseholders are, because remember, the leaseholders is where the reads and the writes happen. So they don't want to have all the leaseholders in one node. And finally, they look at latency. They want the client to have a minimum latency to the leaseholder, so the leaseholders can move around in the cluster. You can configure how aggressive you want this to work, but that comes out of the box. If we look at how this works under the hood, then we have something, we have a shard index. So data split up into these 64 ranges. They're all contiguous ranges, so you can scan them quickly. And then we have this index that maps from what you're looking to onto a specific range. So here we have range 1, 2, and 3, and we're playing with fruits. And so if you're looking for all fruits to begin with B, then you're going to be sent to range 1, and you can quickly understand that it's banana and blueberry. So that's looking at how it works. What happens if a range gets too hot or if it runs out of space? Well, the shard index is updated and it is split into 2. So here we have four nodes instead of 4 ranges instead of 3, and that keeps, when the database grows, this keeps happening. Obviously, the shard index is also replicated, so there's no single point of failure there. I talked about placement, the replication layer here. Each range is going to be at a minimum of 3 nodes. So now we're looking at the node level. I've also highlighted the fact that if you look at the bold and italics, then the leaseholder, that's the leaseholder, and the leaseholders are placed out on 3 different nodes. When I say 3 nodes, that's out of the box. You can configure this to be 7 or 5, 7, 9, how many ever you want, depending on how important your data is. Obviously, there needs to be a quorum in such a system. So if you have 9 nodes, then Cockroach needs to confirm by a minimum of 5 other nodes before it can continue. So it gets more and more expensive. So you would only do that for super important data. What happens if we add another node to the system? Well, there's going to be a rebalancing. So Cockroach looks at that data, and it figures out, I need to split this up a little. It's going to take, in this case, range 3, and start copying that data over from the range, and then it's made live, and you can remove that range from the other node. And this keeps going. It's done in parallel, but I didn't want to do that for animation purposes. So the same for range 2 here. We start copying over, it's made live, and we remove it. So that's how Cockroach will sort this out for you automatically. This is as good as it gets when we have 4 nodes and 3 replicas. Normally, or ranges. Normally, you would, of course, have much more ranges. Okay, let's look at recovery. Let's say we have an outage. What happens in this case? Well, Cockroach realizes that it no longer has a replication factor of 3. It's going to look at what ranges needs to be replicated. Those are replicated over to node 4 in this case, and we can then remove that node from the cluster. Right, so this is out of the box. There's nothing you have to do about it. The next feature I would like to talk a little bit about is GeoCase, or Geo Partitioning of data. With Geo Partitioning of data, it's awesome for many reasons, but in this case, it could be for regulatory reasons or for latency reasons. We basically have 3 different regions in AWS. There's the US West, the US Central, and the US East. Each of these regions will have 3 availability zones, and that's for redundancy purposes. You want to have 3 ACs in each region. And then we can pinpoint data into these regions based, as I said, upon regulatory reasons. GDPR, anyone? California is still started a new data law as well, and I think a lot of states and countries are going to follow suit. So this is becoming more and more important for us as engineers. Okay, how can we do this in Cockroach? Well, when we start a node, we're going to tag it with locality, and in this case, this node is going to belong to the cluster region US East. And then when we define the tables, we decide how we want to partition the data. So there are 2 ways of partitioning. The one is by list, and we're now going to look at the city. So the city is going to determine where the data ends up. So if you live in New York City and DC, you're going to be US East. If you're in Denver or Salt Lake City, it's going to be US Central, and LA and San Francisco, US West. And then you can also define your default, what should happen in a default case, if it's not defined here in the list. Another way of partitioning is if you use ranges. So you can say, out of this data, I want this range to be placed over here and the other range to be placed over there. And what's interesting here is, in this case, we're looking at students. And for students who've already graduated, we don't really care about how quickly we can respond. So we can determine we want to run those on HDD drives. However, for the students who are active, we actually want to use SSD drives. And what you can do is when you start the Cockroach node, you can tag that with attributes. You can say, you are an SSD drive. And then Cockroach is going to figure out how this data should be replicated on that topology. So that's a really powerful way of making sure that the data ends up where it should as well. As I mentioned, Cockroach supports SQL. It implements a large portion, not all of it, the ANSI SQL, but it's close. It uses Postgres, and the good thing about that is there's an abundance of existing drivers out there that you can use, so Gorm for Golang, or Hibernate for Java, and so on and so forth. It comes out of the box with full ACID support. They have invested a lot of effort into something called distributed SQL, and this is if you're querying for data that's distributed, that needs to be highly optimized in order for them to provide the performance that we expect as engineers. Okay, another problem that we run into as engineers is this dual rights problem. In this case, in this complex architecture, we have a service that receives a request, and what we want to do is we want to emit an event to Kafka, but we also want to write to the database. And what could happen here? Well, the database can say, no can do, but we can't really roll back from Kafka. Kafka doesn't support XA transactions. So this is a bit of a conundrum. So what can we do instead? Well, we can turn to the feature called change data capture. And the idea here is that we can still use transactions with the service, the database, and then Cockroach, once it's determined that this is okay, it's going to emit a change data capture to Kafka. And what you do is you actually set this up and you say what tables you want to watch and have events emitted for it. So this is a really powerful pattern, I'd say. And the link I had before to the outbox pattern, there's an open source product called Debesium. And with Debesium, you can actually do this on a lot of databases. So if you're running MySQL or Oracle or what have you, then what they do is they look at the write-ahead log, and they're going to emit events based on the events that happen in the write-ahead log, which is how most databases work under the hood. So you can actually achieve this instead of looking at two-phase commits, trying to solve this in some weird way. You can use this pattern instead. Okay, so is this all gravy then? Are we done? Is this the silver bullet? No. No. There are some challenges with distributed systems, and one of those problems is performance latency. Going single home, having one database to multi-home, multiple databases, always comes with a cost, and I call it the quorum price. And I listed some. Obviously, you already know the latency times, the ping times between different cities, but I wanted to list them here anyway. So Sydney, Paris, 281 milliseconds, which means if you have one node in Sydney and one in Paris, there's no way you're going to get a quicker system than 281 milliseconds if they need to communicate with each other. So that's probably not an optimal solution. And let's say you have a cluster, a global cluster, and you have one node in New York and one in Paris and one in Sydney. It's even worse. So you probably don't want to have that type of architecture. And what Cockroach Labs and suggest instead is to use Geo Partitioning of data. So in the case I just described, we would have 3 ACs in Sydney, 3 in Paris, and 3 in New York. And then the response time would be immediate. Now, why wouldn't we run 3 different databases in that case? Well, from an operational point of view, it's good to have one database, one system you can look at, and the Cockroach dashboard is really awesome. And also, there might be data that you want to replicate the same data over the world, but you don't really care about the latency. It's fine. So for those tables, it's perfectly fine to, or that data is perfectly fine to have these type of ping times. Another thing that's not strictly related to databases but distributed systems is observability. It's very hard and difficult to reason about distributed systems. How many of you are using a microservice-based architecture? Yeah, that's 50, 60%. And so you've already realized this problem where you have different services calling each other and there's an error somewhere. Some services are even asynchronous, so you don't even get a stack trace for a full stack trace. And then you're going to figure out what happened. And it's like, I don't know. I mean, I have service C over here, and that seems fine, but service D said something went wrong. And this is going to be a problem in a distributed system. The way to get around it is to look at companies like Lightstep or Datadog, where they now provide distributed tracing, so you can build a better understanding of what's going on in your system. Right, so I want you to leave here with a few questions to bring home and ponder. Think about baseball. And if you think about baseball, hopefully you think about New York Mets, because that's the best baseball team out there. But if you don't, think about what role you play in the baseball match. So as I showed you, there are different roles in the baseball match, different actors. And you or your company is going to have one of those roles in the baseball match. And it's important to understand that if you go NoSQL, you're going to pay a price. With like full NoSQL, you're going to, yes, good performance, you can build scalable systems, what have you. But you're going to pay a price in that you have to also implement all of that functionality that comes for free if you go fully to the globally distributed SQL databases, where you might pay the price of a little more latency. So maybe you can find a way in between that's good enough for you, where you get the best of both worlds. Another thing is, how scalable do you need to be? Pat's paper talks about infinitely scalable. How many companies are infinitely scalable? Well, I guess it depends on the definition, but maybe Google. I don't know. Not even Google. So maybe, I mean, we're all aspiring, of course, to become the next Google and Facebook, what have you. but maybe we're not, so maybe we can settle with a little less. So therefore, it's important to understand that as well. And another important thing here is, what does your average engineering profile look like? Remember what Google said about eventual consistency? And again, if Google engineers think it's difficult, I think a lot of us are going to find it difficult. How much SQL do you use? How much SQL do you want to use? As SQL, whatever you think about it, it's a ubiquitous language. A lot of us already know it. So it's important to have that as part of the equation. And are you able and willing to use the cloud? If so, there are fantastic options out there. SpannerDB, Cosmos DB, and then, of course, Cockroach. So let this be your machete in the consistency jungle when you go out there. So thank you for listening, and presentation is on speaker deck there.